Okay, so welcome back. So we were looking at different ways of extracting those heavy metals from electronic waste. So we looked at a few of the methods like hydrometallurgical methods, pyrometallurgical methods. So we'll continue our hydrometallurgical method in this particular video as well. We had, if you remember, in the previous video, towards the end of the video, we talked about in terms of the hydrometallurgical process, we looked at halide cyanide leaching and the halide leaching. So we talked about cyanide leaching, halide leaching, as well as what is the limitations of that. And now we will start talking about thiourea leaching. So we'll in this particular video, we'll start with thiourea and some other methods, and then we'll see we'll talk about some of the recovery, how the recovery, some of the case studies, if we can, we'll see based on the time. So in terms of the thiourea, that's another way of extracting the heavy metals like gold. It has been used quite a bit in terms of the recovery of gold from the ore. So it's as I said earlier in the previous video as well, these methods are nothing new. These have been used earlier as well, mostly with the mine like ore. So gold ore, thiourea leaching has been used, cyanide leaching has been used. So they have been used earlier. Now we are trying to use the same technique with electronic waste. So rather than having the ore coming from the mine, like the real mine, we are doing an urban mining. You may hear the term these days, urban mining. Urban mining is essentially looking at all the waste that is being produced and trying to recover resources from there. So that's the concept of urban mining, which you may have heard in some other context too. So in terms of the gold recovery, one of the method is thiourea. Has been used for quite some time. Here in what we do, we'll work with the acidic conditions. In acidic conditions, we try to have thiourea dissolves the gold and they form a cationic complex. So we have a thiourea, which is thiourea. It's the purpose, the way the thiourea works, it is dissolving the gold and it's forming a cationic complex. Cationic complex means it will be positively charged. So and reaction happens very rapidly. Gold extraction up to 99% can be achieved. So that's in terms of the mining activity that we are talking about, in terms of the smelting or the recovery of gold from the gold ore. So if this is in the anode, the reaction that is taking place is you have gold, which is reacting with the thiourea, and then it's getting a positive charged complex. So there have been a lot of research in this area. What are the conditions it works better? You have the rate of leaching. Rate of leaching means at what rate the things will move from the solid phase to the liquid phase. Once something is charged, that means it is in solution. So this particular complex, gold thiourea complex, is in solution. So and so it will depend on the thiourea as well as the oxidant concentration. Now the use of ferric ion is also done, because here a electron is being released. So there should be a electron has to be accepted. As we know, for any reaction, once you release an electron, there has to be a species which can take that electron. So the ferric ion will act essentially as electron acceptor, and then ferric ion ties up with thiourea, with iron thiourea complex, and also depending on the pH condition. So pH is also important. So if you are trying to set up a thiourea leaching of gold from electronic waste, you need to look at iron, sulfuric acid, as well as try to maintain the pH and of course thiourea. So those are the things that you need in terms of getting the leaching process done. So is it being used a lot? How it compares with other? So it's more expensive than cyanide. So that's why you don't see that much of thiourea leaching happening in a commercial scale in gold recovery, in the gold extraction from mine. So it's more expensive than cyanide, but cyanide does produce more hazardous waste. So that's why, in terms of, if you look at in totality, so as I try to explain in my other classes, like in other class, there is another course running parallelly with this course. That course is actually 8 weeks, and it's a as you some of you may have taken it. It was offered last year. It is being rerun this year. It's on life cycle analysis. So there, so that's where why those kind of concepts is important. So here, if you're looking at, okay, cyanide is cheaper than thiourea, but if you look at from a long term environmental costing, long term life cycle costing, when you use cyanide, the waste produced, you have to manage it as a hazardous waste, and that's more dangerous to manage than compared to what is being produced with thiourea. So we have to, if you keep everything of those in place, we don't know, like maybe we'll be trying to we'll find out that actually thiourea comes out to be much cheaper. But again, you have to look at the big picture. You have to look at the whole life cycle of that particular process, rather than just looking at just like a part of it, rather than looking at the whole from the very beginning to the very end. So it's a consumption of its consumption in gold processing is high, because thiourea is readily oxidized. The gold recovery steps requires more development. Still things are in under development in this particular area. Cyanide is a older process, more established process. People have looked at that process in a more for many years, as opposed to this one is a relatively newer process. Is still kind of work in progress in there. Then the other is thiosulfate. Thiosulfate leaching also happens. Here the gold is the gold is dissolution happens in ammonia thiosulfate solution. So that's what you are seeing over here, the copper NH342 plus. So that's the solution where copper is there and ammonia is there, and as copper has a tendency of actually in the presence of ammonia, copper has a tendency to produce soluble complex that we have seen that in some of our other research as well. So it's it's copper ammonia complex. They will since it's a positively charged, it will acquire electron, and then it will get reduced. It will be reduced, and then at the same time either ammonia and thiosulfate ion will react with gold and to produce gold ammonia complex or gold thiosulfate complex. So it's then you have gold in solution now, and then you can try to find out extract gold from the solution. So any leaching, this is again another leaching process. So leaching process, as you know by this time, leaching means moving of things from the solid phase to the liquid phase. So here also our goal is to get the gold out of those electronic waste and then into the solution, and then we can try to recover gold from a solution which is enriched in gold. Right now it's in the solid form, so extracting that from solid to the liquid, and then finally to get the pure gold out of that. So it's depending on the thiosulfate or the ammonia copper complex, you may have either it will convert to copper thiosulfate and ammonia. So in the presence of thiosulfate and ammonia copper complex, what happens is essentially a change of place. So thiosulfate will react with copper, and then it will make a complex with copper thiosulfate complex, and so ammonia will be free, and then it will be ammonium it will make complex with gold, and then it will bring it to solution. So and at the end, both the copper thiosulfate and the copper ammonia species, they oxidize to copper ammonia complex again. So that's how the process works. Here the reaction has been presented. Again, these reactions and other stuff, I'm not expecting you to memorize. It's not that this is not a memorization test, so you don't have to memorize. Even if those of you are planning to take an exam on this one, you don't have to memorize all these equations. You try to understand what is the process that is happening there. So just to give you an idea that things, what are the complexity which goes into recovery of gold from electronic waste. And those of you who are from a chemistry background or a chemical background, or possibly wants to set up, or anybody who possibly wants to set up a like a process where we can recover this gold, because right now what is happening in terms of the e-waste management, I was trying to explain earlier, most of it goes to informal sector. Informal sector cannot actually manage it in it properly. There are a lot of environmental impact, human health impact. So, if there is a nice merger of informal and formal, and if we can set up some of these plants in a formal atmosphere, in the formal sector, which we can recover some of this gold and other stuff, which will be which can be done in more efficiently. So, these are the how it needs to be done, how things have been done in other countries and other places. So, this is just to give you an idea of what are the different methods. We looked at different types of extraction. So, this is either you go for urea, thiourea, thiosulfate, cyanide, halide, all these are different methods. They work under different pH conditions, they work under different operating conditions, and then they have different efficiencies as well. So, if we want to decide which one to use, of course, we have to look at the efficiency of the process, the cost of the process, and then when we say the cost, my request to all of you from now on, that whenever you look at the cost of anything, look at total life cycle cost. Don't just look at the cost from a short term, because the short term cost is not the real cost, and doesn't matter whether I'm talking about in general, not only for e-waste. For in general, when you look at the cost, look at the total life cycle cost of that particular process or particular product. So, because environmental degradation, resource depletion, they are all because that will be that's a big thing actually in today's world, with all this climate change, sustainable development goal, and all those things that we talk about. Unless we start implementing that in our day-to-day practices, we are not going to go anywhere in terms of the environmental betterment of environmental performance. So again, looking to this long reaction, I am not expecting you to remember of this reaction. I just want you to understand that how the things work. So, in the presence of you will have thiosulfate and copper ammonia complex. There will be exchange of ions for that matter, and thiosulfate will go with copper, ammonia will get free, ammonia reacts with silver and then gold, and it brings gold and ammonia complex in solution, and then we can recover our gold from there. So, this is how typically the scenario work in terms of thiosulfate leaching. In terms of say any process has certain advantages, certain disadvantages. So, it's a gold thiosulfate complex is fairly stable, which is a it's a stable complex. pH of around 9 and 10 is preferred, because that's the because it's and generally preferred especially at ambient temperature, because thiosulfate appears to be less prone to degradation, as well as the copper ammonia complex is more stable. Ammonia, as you probably know, ammonia typically you will see at the pH above 9. Anything below pH 9 you will see that in ammonium, you will see in NH4 plus. When you try to see NH3, that will happen only when the pH is above 9. So, that's why you see the pH of 9 and 10. So, again, if you have to don't try to memorize things, try to understand that why pH 9 10 will be preferred. It because the copper ammonia complex is more stable. Ammonia will be in the form of ammonia only when the pH is above 9 or around that particular pH. Anything below that, it's mostly in ammonium, NH4 plus. So, you will not see it. And if you know that ammonium chemistry, it's obvious that you will say that of course you need to have pH 9 and 10, otherwise you will not see copper ammonia complex. So, that's how you need to you should approach, rather than trying to memorize. And then of course, if you try to memorize something without understanding, it doesn't stay for long in your head. So, and then those are the kind of advantages point of view. In the terms of disadvantage, the principal problem is it's a high consumption of reagent during extraction. So, you need a lot of thiosulfate, and there is a loss because there is around 50% of the thiosulfate, it's a ammonical thiosulfate solution. Copper also has some reactions going on. So, 50% of the thiosulfate kind of goes there, and so it's not a very efficient process. So, that's it's a loss of around 50% of thiosulfate happens there. So, and it's a slow process, and it's a lot of consumption of, so it becomes uneconomical in spite of their potential environmental benefit. So, although it's better from an environmental point of view compared to cyanide leaching, but since it's a lot of reagent consumption, that makes it things uneconomical. So again, you have to look at the life cycle cost. Here the bullet, second bullet which you see over here, I'm not sure whether that incorporates the life cycle cost, because we have to look at the how much money that goes into managing that cyanide containing waste, because that may be much higher than rather than going for this thiosulfate leaching. And there is a, in terms of at present there is no simple and affordable method recover gold from thiosulfate leach. So although we are bringing it to the thiosulfate solution, now how to get it out from thiosulfate solution, that also is a question. That also, because ultimately our goal is to get the pure gold. So to get the pure gold, I have to take it out of that thiosulfate solution. So the method, the process for that is also under kind of a lot of there is no simple and affordable method of doing that as well. So that's to give you some idea about in terms of the different extraction methods. Then we'll look at some of these extraction of precious metals from the leaching solution. So far we have been talking about how to get this into the leaching solution. So if you remember, in terms of the extraction of the precious metal, the step one is to, because everything is in the solid form. So the step one is, let's bring this the precious metal from the solid form in e-waste to the liquid form. So let's bring them in solution. So let's try to get them in solution by all these hydrometallurgical process, pyrometallurgical process. So and that's how these processes works anyway. So you bring it into the liquid form. Now when they are in the liquid form, we try to, next obvious step is to, now let's get these individual metals extracted from this liquid form, which is called the leaching solution, because what we have been doing so far is the hydrometallurgical leaching or the pyrometallurgical leaching. Now we want to get things from the liquid form into the pure solid form. So that's let's look at some of the mechanisms, some of the examples of how that is done, because that's also an important, that's like an important follow-up step. So in terms of getting the precious metals from the leaching solution, there are different ways you can go about it. Again, similar things have been done by the metallurgical friends for different applications. So you can go for cementation, you can try to, we'll go over each one of them. Go for solvent extraction, adsorption on activated carbon, that's another one, and then ion exchange. So those are 4 mechanisms which potentially you can go for. Now what is the cementation? There has been it's a pretty old method since almost 140 years ago, 130 years ago. Zinc cementation has been used. So once you have the cyanide solution in which from the gold ore, when you have the gold in the cyanide solution now, so zinc cementation is used to recover the gold from the cyanide solution on a commercial scale. This process has been explained nicely by Merrill and Crowe, so that's called Merrill-Crowe process. The major reaction here, especially in cathodic deposition, is a gold and anodic corrosion of zinc. So in cathode, we say the gold gets deposited. So that's how the reaction takes place. So that's the cementation reaction of zinc cementation is used to recover gold from. It's a pretty old method. So major reactions here is we have the gold with the cyanide complex. As you can see on the first reaction, gold and the cyanide complex is there, and then you add so you basically have a reaction where it gets further reduced, where you have the gold gets separated with cyanide, so cyanide ion, and then the zinc reacts with the cyanide ion and makes zinc cyanide, and so that's how the process works. So the cementation of gold is practically constant. You work at the pH range of 8 to 11. Here are so it's a some problematic is also there in terms of if you have impurities of lead, copper, nickel, arsenic, antimony, and sulfur, they have a chance to they are deleterious for gold cementation. So they also react in this particular scenario and they create some impurities. So that's one process in terms of cementation, and it has been reported that gold from thiourea, thiosulfate, thiocyanide, so you can use that. You can also use the reduction precipitation with the sodium borohydride. So, sodium borohydride is also used, which is 12% by weight of sodium borohydride and 40% sodium hydroxide. So, that is also used as one of the recovery of gold. So, it can be reduced effectively to metallic gold from in addition of sodium borohydride at ambient temperature. So, it is a thiourea, it is a alternative leaching from gold bearing, but also a stripping agent for gold from loaded solvents and reagents. So, thiourea does happen very thiourea is kind of works good along with cementations for recovery of gold from the electronic waste. So, that is in terms of looking at how to get the precious metal out from the solution. That is one we saw. What we saw so far is in terms of getting things into the solution. The other same thing we can do by solvent extraction as well. So, we can do some sort of solvent extraction. We will look at some of the example. So, there have been studies where they have tried to have the gold in thiosulfate solution extracted with alkylyl phosphor ester. So, you can have alkylyl phosphor esters being used, which can so if the gold is more soluble in that particular ester, alkylyl phosphorus ester, the gold will get more solubilized over there, and then it will go from thiosulfate solution. So, ammonia has also affects gold from thiosulfate solution with alkaline phosphorus ester. So, that is there, and there is a mechanism, the extraction mechanism is there in the presence of ammonia and also in the absence of ammonia. Both mechanisms are is available in the literature. So, the system with the no ammonia, you will see some sort of the reaction as you see on the first bullet. So, you will have sodium is there, then you have gold, and then thiosulfate hydroxide, and you have like a in terms of your what would we say, like a precious metal by the solvent, which is using the alkaline phosphorus ester. So, that is what you see, like phosphorus ester as being used, and you make a complex which is a sodium, gold, thiosulfate and hydroxide with some ester which is there, and so that is one in terms of like a complex. And if you, in the absence of ammonia, if the ammonia is present, again similar reaction takes place, and then we have ammonia also in solution over here. So, ammonia also is in the complex. So, here the I and J can vary, as we can know, and that coefficient like ester coefficient in the two equations are in the range of 1.5 to 2.5, and pH is around 6 and 9 or something like that. So, that is it's based on that we use this particular solution for extraction, and so that's that's how you can do some a recovery of gold from different like a liquid. So, as I said earlier, we have this liquid which first we have the groups on e-waste, which is in the solid form. We have some of this precious metal. First step, we try to bring this precious metal into the liquid phase. In the next step, from the liquid phase, we try to bring it back into a solid phase, but more in a pure form. So, that is the goal in terms of this method that we have been talking right now. So, other ways, activated carbon again it will work with adsorption, because that is what it does. Activated carbon has good like a particle, like a small particle size, bigger surface area, and good adsorption sites. So, there is a mechanism of kinetics of gold from solution has been investigated, many people have looked at. So, they have isothermal expression where the Q is equal to Q max, where the Q times a certain factor, which is BC upon 1 plus BC, which is explained over here. So, what is Q and Q max and all that? So, Q is the quantity of solute absorbed per unit weight of carbon, Q max is the maximum sorption capacity, C is the equilibrium concentration, and A and B are the adsorption equilibrium constant. So, they are the factors which we need, which we use. So, this is activated carbon, as we know, it is a works on the principles of adsorption and different isotherms, that is what we have bin looking at here. So, it is another expression we can explain this either as the Freundlich isotherm. So, Freundlich isotherm, again some of you maybe I assume that many of you will be familiar with that. So, you can put another expression we can put is the Freundlich isotherm. Freundlich type multi-component isotherm is also there. So, which is presented in the small bullet. Again, you do not have to memorize all of these. What I am trying to say is just trying to show you that whatever we learn in different courses. So, with the different courses that we take, whatever we learn, they do get applied somewhere. So, if you remember that these like activated carbon, isotherm, Freundlich isotherm, and other in terms of the multi-component isotherm. So, all these things you have taken this, especially if you are a master's or a PhD student, you already have done this kind of like basics of some of these terminology in some other courses. But what I am trying to show you here is all these concepts that we learn in different courses are actually really applied. So, always think one thing, if you can trust me, whatever we learn from say high school or even from before that, from middle school all the way to say college and other stuff, most of the stuff that you learn is for some purpose. It's not for fun. So, it's there to make you learn some of the new stuff which you will use it at some point or the other. You may not realize it when, and but you will use that knowledge in some form or the other. So, that's with that message, let's close this particular video. So, we will continue our discussion in the next video where we will talk about more in terms of these leaching process and essentially how to get this gold and precious metal which is there in the liquid phase now. It was earlier in the solid phase in the e-waste. We brought it to the liquid phase by different extraction methods which we explained so far. Now, we want to get it back into the solid phase and in a pure form. So, how we can do that? So, we will keep on talking about it in the next video as well. Thank you. Keep watching, keep following up, put questions, concerns, or whatever you want to communicate with us on discussion forum. We will be more than happy to answer. Thank you.